Let's get started on 2.2, which is on limits of functions and then the limit laws. So 2.2 is the more intuitive idea of considering or looking at limits. So this is on finding limits graphically and numerically, and it's frankly a warm-up to a more rigorous definition of limit, and I'll talk about that as we go. So this one I want to get across what we mean by a limit, and show what it looks like graphically, and I'll show you a numerical example of just basically substituting or plugging in numbers. Okay, so go ahead and write all that down, finding limits graphically and numerically, and that this is more of the intuitive idea of limits. So first, let's consider the function. So consider the function. Let's take f of x equal to this rational function, x cubed minus 2x squared all over 3x minus 6. So without manipulating that function at all, what happens as we get close to a number? Now you may be able to recognize you could factor the denominator out, the 3 out, and then you factor an x squared out and be able to simplify it. But as it sits, we still have an issue at a certain number. So what number is that? So here's the question. Here's what we want to look at. So the question is, f of x gets close to what number? So the function value gets close to what number as x gets close to 2. Now, do you see why I'm asking about 2? If you put 2 in there, what happens? Yeah, you get 0. So that's a problem. But without manipulating and talking about that, let's just see. So we're not going to substitute in 2. So we're going to do, this is numerically, so we're going to do a direct calculation. So direct calculation and see what happens. So, and the other thing we want to talk about is, see, this isn't very well defined. What do I mean by close mathematically? Okay, that's what we're going to define in the next section about the precise definition of limit. So what we're going to do is set up a table, and I'm going to show you what the table looks like, and then I'm just going to copy it over. So you're going to plug in x, you're going to evaluate f of x, and we'll do two lines, so it'll look something like this. Okay, so I'm going to pull up the chart in a second. So we're going to pick values. So we're going to get close to 2, but not exactly 2. And then evaluate the function. So if we plug it in, substitute in, and you evaluate at 1.9, you get that value. If you evaluate at 2.1, you get, and I'm not doing this in my head, I have this pre-worked out, you get this value. Okay, so I'm going to erase that and pull up the actual chart. So you keep doing that, getting closer and closer to 2 without, without equaling 2. And then we'll make a conjecture what it is. Okay, so I'm going to erase this now. And down here I have a nice table for us to pull up. So we'll just pull this table up. Okay, so pause the video and write this table out. If you're willing, actually substitute in the values of the function, right? You're going to do f of 1.9. Do your calculation, and you'll get the 1.20333, etc. So you do all those, and you get this table. So as you're substituting the values, you're getting these values out, 1.3, and this looks like it's 1.3 repeating. Okay, so if you evaluated f at 2, what are you going to get? You're going to get undefined, right? So basically, the thing is, we're not talking about at 2. That is undefined. So we're not going to substitute in f of 2. But as you approach it, what are you getting close to? That's the idea. So 1.3 repeating, though, is what? That's 4/3. So what we say then is, this is the intuitive idea, right? So it appears that as x, and then remember that arrow, if you haven't seen that before, means approaches. So as x approaches 2, f of x approaches 4/3. Okay, so now if you were to graph, this is how you would actually graph f. So graphing f, we have f of x equal to, you can just pull that down, f of x equal to x cubed minus 2x squared all over 3x minus 6, and then we factor. This is where we can actually simplify it. X minus 2, factor numerator, factor the denominator, factor out the 3. You're left with 3 times x minus 2, which is equal to x squared over 3, provided, now you can't just cancel that out, right? You can't just like, oh, it's gone. No, you can't do that. We have to say x cannot equal what? It cannot equal 2. So it's not part of the domain of the function. Anyway, but we can still talk about a limit as you approach 2. So that's what you get. And you can see then, well, let's do graphing. So you're actually graphing this function. So this is just a parabola. So if we graph that, let's do it down here. We get this function. Okay, and it's just, so at 2, and we'll just do whatever scale, it doesn't really matter. So you do 2, and then you're going to be up at 4/3 right here. So that'll be 4/3. Let's change colors, make it look pretty. So you get this parabola, not to scale, of course. But what do I have right here? What's right there? Okay, that, of course, is the hole in the graph, and I gotta make this partial. Okay, so there's a hole there, so you just make it look like a circle there, like that. So what we're doing then is we're coming in on 2 like this. We're coming in on 2 from both sides, and we're seeing what happens to the function. Now, we're not requiring the function to be defined there. We're just asking what value does the function approach. So graphically, you can see here as well. So graphically, we see the same thing, that f of x is equal to 4/3, approaches 4/3. Approaches 4/3 as x approaches 2. Okay, and as I already mentioned, the function does not exist. D&E means does not exist at 2. So the general concept of limits looks like this. So let's go down here. I'll leave that up a little bit longer. So let me write this out so you have the general idea. So this is what we call the general concept of limits, or intuitive idea. So one is kind of what I've been saying. Let me move this up so you can see it better as we write. So we want to know as x gets close, and then we'll define closeness later. So as x gets close to a, but not equal to a, but x does not equal a. So this is the question you're asking. Does the function value get close to some number? Okay, so some number, anyway, you call that number L. Some number L. Okay, so that's what we're asking. And then 2, that's one way of thinking of it. This is another way of thinking of using more of the language we're going to use for the definition. So the next one or question is this, and the way to think of it is, can we make the function value of f of x as close to L as desired by choosing x sufficiently close to a, but not equal to a. Okay, that's the question. Let me read that again, because this is more of how we'll write the definition. Can we make the function value of f as close to L as desired by choosing x sufficiently close to a? That's the direction of the logic, if you will, of what we're going to look for. If we say yes for 1 and 2, so if yes for 1 and 2, well, it's actually or. Like, they both really mean the same thing, 1 or 2. So it's the same. Put it like that. We write this notation. We write the limit, LIM for limit, of f of x as x approaches a equals L. So we're saying that the limit equals L. That's the idea. So if that's the case, then we have that limit. Let's see if I can make that look like a box. Sure did, yay. You can move it and make it fit exactly on there. So the next few things we'll do is define what that means and look at a few examples. So I think I'll do another video. I don't like to make these too long. And I'll do a couple examples, and then the rest of the examples we'll save for the problem sessions next, when we do them. I'm trying to make these more generic now, so when we get to them. Okay.